Welcome. My name is Rogério, and today I'll be presenting CODBS, Cascading Oblivious Search Protocol for Real-World Relational Database Indexes. As the majority of people attending this presentation probably already know, database systems are widely used to store data across many different types of applications and use cases. For example, if you go to the hospital or a clinic and schedule an appointment, your data will be stored on the database system. If you do some online shopping, if you use a social network, or if you simply send a message through a messaging application, your data will be stored on the database system. And there is here clearly a fundamental privacy problem because we willingly provide our data to online services that end up storing our data in databases, but database systems were not designed to be secure or to ensure the privacy of our data. They were designed to be durable, consistent, and efficient. Additionally, as we increasingly rely more on cloud services to host database systems, there is here a big problem as cloud services become a common source of attack, and this has resulted in multiple data breaches. For example, more than 1,000 data breaches per year just in the US, which also results in loss of revenue for organizations and even has a direct impact on individual users. And the big question is, how can I improve the security of database systems? Well, the research community has proposed cryptographically protected database systems, where the main idea is to keep the data encrypted at all times during storage and during query computation. At a high level, we have a trusted site and an untrusted site. On the trusted site, we have a database client, which has access to its own cryptographic keys and encrypts data before sending it to the database engine. The database engine is hosted on an untrusted site and evaluates queries and stores the data on the database storage. However, the untrusted site is compromised by an adversary that wants to learn as much information as possible and the contents of the database engine. This solution of cryptographic protected database systems seems like a good solution for handling this attacker or this adversary, but there are still a few issues that need to be addressed. One of them is the access pattern discloses during searches over relational database systems. On relational database systems, we generally have database tables and database indexes that improve the search time of queries over the indexes. For example, the most common use case is to use search trees to improve search time over database table. However, even if the data is encrypted, any search over a search tree on encrypted data still follows a deterministic access pattern, which will access a few subsets of data nodes and a subset of database table records. And this access pattern actually needs to be addressed and protected somehow, as it can be possible to reconstruct the actual encrypted values just by observing this information leakage. One possible way to address this issue is to use ORAM encryption schemes, where the core idea is that we have an encryption scheme that, given a request to read or write a data block in an array-like data structure, as we see here on the server storage, where you have multiple addresses, each one storing data contents, the actual operation done on this server storage is hidden from an attacker. And this is possible by having the client a stash, which stores the most recently accessed nodes, and a position map that basically assigns each address on the array that's hosted on the server storage a random arbitrary position. And anytime that you want to actually access a real position, for example, this cell, we actually send multiple requests to access, for example, fake data or data that is not related with our real value that we want to access. And by doing this, we can actually hide the real traffic in the process of doing multiple accesses that are not directly related. And our goal and our contribution in this paper is to apply these concepts of ORM encryption schemes and improve on them on the context of relational database systems and optimizing the data structures for Oblivious searches, more specifically on database indexes. And so we propose CODBS, a cascading Oblivious database search protocol that has minimal information disclosure, as a practical performance with reduced bandwidth blowup, and is actually suitable to be used on trusted hardware, which is another factor that we consider. Additionally, we implemented a prototype on top of Postgres and did an experimental evaluation with YCSB. Now, let's take a look at the actual contributions that we do. But first, to understand them, let's redefine a little bit better the actual problem setting that we consider in our paper. As we presented before, we have a client-server model with a trusted site and untrusted sites. The trusted site holds database clients, and the untrusted site, the relational database engine. However, now the untrusted site also has this special trusted hardware module. We can think of it as an isolated container where we can store our own data and code without being accessible from an external context like an hypervisor or an operating system. The access to this trusted hardware module is only possible by using specialized hardware instructions which are not accessible from an external context. And additionally, these specialized instructions ensure the confidentiality and integrity of the data stored inside of the trusted hardware module. As you can imagine, this trusted hardware module is really useful to offload some computation, but we also have an adversary that wants to learn the contents of the database data and will use any information available. And so, to be even a little bit more precise, we consider a semi-honest adversary that can observe all communication and computation on trusted sites, with the exception of what happens inside the trusted hardware module. However, the trusted hardware modules are not perfect, and they actually disclose the access patterns of fetching data from the main memory and from accessing the external storage. And so they don't tackle our fundamental problem of hiding the access patterns of the database if you want them. And now the next question is, given this problem setting and trust model, how do you actually design a cryptographically protected database system that can simultaneously hide the access patterns of queries on the database system, leverage trusted hardware, and provides efficient queries over the data? Well, the straightforward approach, which you can find on the state of the art across different papers, is to offload as much computation as possible to the trusted hardware, or in this case, the trusted proxy. On the storage backend, we keep the database table and database index, but now on the trusted proxy, we actually have a component that can intercept client requests, fetch data blocks from storage backend, and evaluate queries over plaintext data. And if we look a little bit closer, we can also even find systems that use ORM encryption schemes to access the database table and hide the access patterns. And the same can also be applied for database indexes. This is actually a common approach that we will call it the baseline, and we will actually use it later on the evaluation. But for the actual use case of accessing database indexes, there are of cryptographic algorithms that are more specialized and suited for these operations. And they are known as Oblivious data structures, where they generally build on top of ORM encryption schemes, and instead of just providing a read and write API, they provide an API to insert nodes and to search over the data on the Oblivious data structures. And the core idea is to have a single monolithic ORM scheme where an entire search tree is stored inside of this ORM encryption scheme. And to actually search the data, we keep on the client, for example, the trusted hardware, a tree root pointer to the first tree roots of the search tree. And so we take this pointer, we fetch the first block on the ORM encryption scheme, and then search for the next shell nodes. And notice here that the tree root and any other node of the search tree actually keeps on the ORM the pointers to the next shell nodes and the position maps to the next shell nodes. And so we only need to look at this data, and we find the next record that we need to access, and do this step recursively until all 3 levels are accessed. At the end of a search on a tree-based Oblivious data structure, we actually need to do 2 things. First, update the child position maps for the next access, and secondly, shuffle the data blocks on the ORAM and flush them back to the storage. And these 2 steps actually have to be done in sequence to ensure the Oblivious guarantees and properties are provided for the next search queries. And while this is actually a first good step to hide the access patterns of search queries over relational databases, there are still a few limitations. One of them is that the ORAM encryption schemes are used as black boxes, and they are not optimized for relational database systems. Secondly, Oblivious data structures overhead grows with the number of nodes stored in the ORAM, and for big search trees, this can actually be a significant problem. And finally, trusted hardware modules have a limited memory size, so we need to actually minimize the amount of information that we store and process inside the trusted hardware modules. And our solution, given these limitations, is to actually propose an optimized Oblivious data structure for a relational database system. And this is where our cascading Oblivious database search protocol comes in, and the actual proposal that we have made. And our idea is quite simple. Actually, we simply divide this large monolithical Oblivious data structure in smaller Oblivious, in smaller ORAM encryption schemes, such that each ORAM encryption scheme has significantly less information than the big monolithical ORAM encryption scheme. And if you notice in this image, we actually have one ORAM encryption scheme for each search tree level. And another thing that is different is that now, instead of having static position maps inside each tree node, we have counters. And these counters are actually dynamic, and we also have a root counter for the tree roots, and they're actually updated after each access. And by combining this division of splitting the ORAM encryption scheme and the root and the dynamic root counters, we can actually decrease the overhead of accessing nodes on the search tree. We have significant practical performance improvements, and each tree level can actually be accessed independently without having to wait to access every level to update the position maps and then shuffle and flush all the data nodes to the ORAM encryption schemes. So we have several improvements to this approach. And just to give you some high-level idea on how the search of our cascading Oblivious database protocol works, is fairly similar to the standard Oblivious data structure and to a search tree, where we have the root counter and we access the tree roots, and then we find the counter for the next shell nodes, and so we can actually access the next level. The only difference here is that we use a pseudo-random function to calculate an arbitrary position on the shell nodes, which is done using the counter, some additional information, and a secret key that is hosted inside the trusted hardware module. And this change is actually very significant because now we can access each level independently and update it after finding the node that we have, and we don't need to access every level, and only then upload or update the position maps and flush the nodes. And so this allows us to reduce the bandwidth blowup from log n to the power of 2 to L to the power of 2 divided by 2. And we have used this idea and implemented on an optimized Oblivious database system architecture, which we presented here. It is fairly similar to the baseline that we originally presented, but we now notice that the trusted proxy or trusted hardware module has been instantiated as an Intel SGX enclave. Additionally, now we only have the logic to access the database table and the database index by using the optimized ORAM encryption schemes and optimized Oblivious data structures. And if you notice on the storage backend, now we have flushed most of the data to there, where we have some stashes and position maps when needed, for example, to access the database table, and the stash of accessing each data structure. And this combination actually allows us to access the protected map, to access the stash and position maps in an oblivious way. So we don't disclose this information to the adversary either. We minimize the data stored in the trusted hardware to small context, and we reduce the bandwidth blowup of accessing the ORAM encryption schemes. We implemented this system architecture and the CODBS protocol on PostgreSQL as a server-side extension, and we support equality and range queries. And on this prototype, we actually support B+3 as Oblivious data structures to index database tables. And additionally, we implemented an ORAM library that provides a high-level and simple API that can be used to access any database structure, and actually has implemented the CODBS protocol that we have here as well, and made it open source in these two projects that you can easily use. To evaluate our prototype, we actually use YCSB with two custom workloads, workload A for equality search query and workload B for range queries. And the goal of our evaluation is to actually validate the prototype feasibility and measure the overhead of Oblivious searches queries with CODBS. And additionally, we compare our performance of CODBS in comparison to the baseline architecture that we initially presented, when we also implemented this baseline using state-of-the-art Oblivious data structures and ORAM encryption schemes such as PAT-ORAM. And with the evaluation, we actually find that our system is 4 times more efficient on workload A than the baseline system, and 3 times more efficient on workload B. And additionally, we see that the access time of our protocol is mostly spent accessing the database table, and only a small percentage of the time is spent accessing the database index. And we actually see this slightly better in this query breakdown, where we measure the execution time of each system, the baseline and the CODBS solution. And we see that on the baseline, we spent more or less half of the time accessing the database storage for the database index, and half of the time accessing the database storage for the database table. However, on the CODBS protocol, we see that you actually spent a smaller percentage of the time accessing the database table, and we significantly reduce the time spent accessing the database index on the database storage. So actually, the most of the time is spent accessing the protected memory of the trusted hardware, which is significantly faster, and we have less I/O calls to the external world and less I/O calls to the actual external storage. And this actually explains pretty well why our CODBS system is more efficient in practice, and also that we spent less time writing and reading data on storage. And this is actually a good improvement. And to conclude, we show that there are still possible optimizations on cryptographic database systems that can be done, and don't necessarily need to disclose more information or disclose the access patterns of queries. We show that our protocol is up to 4 times more efficient than state-of-the-art Oblivious data structures and the baseline solution that we presented. Additionally, the information disclosed of such queries is limited to the database size, and we have proven this with a game-based security model that we don't present in these slides, but it's available on our full paper. And you can actually extend our CODBS protocol for additional relational operations like joins, aggregations, and group bys. This concludes the presentation. Thank you for your time. If you have any questions, please reach out to me, and I will be super glad to be able to help you. And I hope that you have enjoyed the presentation. Thank you for your time.